CIET NCERT presents audiobook Ganit Prakash, Part 2, Textbook of Mathematics for Grade 7.
Chapter number 6. Page number 136. Constructions and tilings. On the right side of the page, you are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. 6.1. Geometric constructions. Eyes. Do you recall the eyes construction we did in grade 6? Here we have two different pictures of eyes in which one is black and white and the other is colored. It appears as they are the eyes of a dancer. Of course, eyes can be drawn freehand, but we wanted to construct them so that the lower arc and upper arc of each eye look symmetrical. We relied on our spatial estimation to determine the two centers A and B, find in figure, from which we drew the lower arc and upper arc respectively. The arcs define a line XY that supports the drawing, though it is not part of the final figure. We can start with this supporting line and systematically find the centers A and B. For the eye to be symmetrical or for the supporting line to be the line of symmetry, the upper and lower arcs should have the same radius. In other words, we must have AX is equal to BX. Since AX is equal to AY and BX is equal to BY, this means AX is equal to AY is equal to BX is equal to BY. Here we are also provided a picture of the arcs made with the centers A and B and with the line XY. Page number 137. How do we find such A and B? From X and Y, draw arcs above and below XY with the same radii. The 2 points at which the arcs meet above and below XY give us A and B respectively. Use this to construct an eye. Here we are provided with a picture in which we find XY as a given line, and with the help of this, two arcs are cut over and under the XY line segment to get the points A and B. In figure 6.1, join A and B with a line. Where does AB intersect XY? And what is the angle formed between them? We observe that AB passes through the midpoint of XY and is also perpendicular to it. A division of a line or any geometrical object into two identical parts is called bisection. A line that bisects a given line and is perpendicular to it is called the perpendicular bisector. On the right side of the page, we are provided with a figure in which we can find XY line segment, and with the help of X and Y, arcs are made over and above XY line segment and points are marked as A and B. On joining this line A and B, we get a point of intersection O with line segment XY. Will the line joining the 2 points at which the arcs meet above and below XY always be the perpendicular bisector of XY? That is, when XY is of any length and the arcs are drawn using a radius of any length. This can be answered through congruence. Let us consider a line segment XY. Find points A and B such that AX is equal to AY is equal to BX is equal to BY. Draw the lines AB, AX, AY, BX and BY. Let O be the point of intersection between AB and XY. Which two triangles should be congruent for AB to be the perpendicular bisector of XY? That is, O is the midpoint of XY and AB is perpendicular to XY. If we explain that triangle AOX is congruent to triangle AOY, then OX is equal to OY and angle AOX is equal to angle AOY because they are corresponding parts of congruent triangles. Since angle AOX and angle AOY together form a straight angle, we have angle AOX plus angle AOY is equal to 180 degrees. Thus, angle AOX is equal to angle AOY is equal to 90 degrees. This establishes that O is the midpoint of XY and AB is perpendicular to XY. On the right side of the page, we are provided with a picture in which we have XY as the line segment, and on making arcs for point A and B with the perpendicular bisector, we find that there are two triangles formed, triangle AOX and triangle AOY. We have the common side as AO. The two triangles have been colored in different colors, green and yellow. Page number 138. In triangle AOX and triangle AOY, we already know that AX is equal to AY and AO is common to both triangles. If we can show that angle XAO is equal to angle YAO, then by the SAS congruence condition, we can conclude that the triangles are congruent. To explain this, we observe that triangle ABX is congruent to triangle ABY. This is so because AX is equal to AY, BX is equal to BY and AB is common to both the triangles. Thus, we have angle XAB is equal to angle YAB or angle XAY is equal to angle YAO because they are corresponding parts of congruent triangles. Hence, AB is the perpendicular bisector of XY. On the right side of the page, we are provided with a picture in which we find XY as the line segment and AB is the perpendicular bisector of XY meeting at point O. We also have four triangles formed here: triangle AOX, triangle AOY, triangle XOB and triangle BOY, in which sides AX, BX are equal, AY and BY are equal, and we also have XY as the line segment with AB as the common side. One triangle ABX is colored green and other triangle ABY is colored yellow. We can have eyes of different shapes. Here we have pictures of different eyes. In fact, they have different shapes. Some are oval in shape, having circles at the center, and some have concentric circles in the middle of the eyes. Some eyes are circular, having concentric circles. Some eyes are of a statue. Some eyes appear to be of some cartoon. Page number 139. How do we get these different shapes? Try. One way is to choose two other points C and D such that Cx is equal to Cy is equal to Dx is equal to Dy. An eye of a different shape can be drawn using these points. Will C and D lie on the perpendicular bisector AB? The points C and D are at the same distance from both X and Y. We have just observed that joining any two such points gives the perpendicular bisector of XY. Since XY has only one perpendicular bisector, which is the line AB, the points C and D must lie on the line AB. On the right side of the page, we have a picture of an eye with two endpoints X and Y. With the help of points X and Y, we have arcs cut above and below the line, meeting at points A and B. Likewise, we have another set of arcs meeting above and below the line with the points C and D respectively. Justify the following statement using the facts that we have established. Any point that has the same distance from x and y lies on the perpendicular bisector of xy. Thus, eyes of different shapes can be drawn by suitably choosing different pairs of points on the perpendicular bisector as centers to construct the upper and lower arcs of the eyes. Construction of perpendicular bisector. Given a line segment xy, how do we draw its perpendicular bisector using only an unmarked ruler and a compass? We have learned that joining any 2 points, one above xy and one below, that are at equal distances from x and y, gives the perpendicular bisector of xy. This gives a method to construct the perpendicular bisector. First point, take some fixed radius from x and y. Construct two sufficiently long arcs above xy. Name the point where the arcs meet as A. Here, on the right side of the page, we have a picture of a compass with a pencil inserted in it. And on the same page, we find another line segment xy with two arcs meeting above the line at point A. Page number 140. Second point, using the same radius from x and then y, construct two sufficiently long arcs below xy. Name the point where the arcs meet as B. Third point, AB is the required perpendicular bisector. On the right side of the page, we have a picture in which we have line xy and two arcs are made from point x and two from point y, one above and one below the line segment xy at points A and B. And AB is the perpendicular bisector for the line segment xy. Thus, the perpendicular bisector can be constructed using the simplest geometric tools, an unmarked ruler and a compass. We will use only these two tools for all the other geometric constructions in this chapter, unless there is a need for drawing lines of specific lengths in standard units. Figure it out. Question number 1. When constructing the perpendicular bisector, is it necessary to have the same radius for the arcs above and below xy? Explore this through construction and then justify your answer. Hint number 1. Any point that is of the same distance from x and y lies on the perpendicular bisector. Hint number 2. We can draw the whole line if any two of its points are known. Question number 2. Is it necessary to construct the pairs of arcs above and below xy? Instead, can we construct both the pairs of arcs on the same side of xy? Explore this through construction and then justify your answer. Question number 3. While constructing one pair of intersecting arcs, is it necessary that we use the same radii for both of them? Explore this through construction and then justify your answer. Question number 4. Recreate this design using only a ruler and compass. On the right side, we are provided with a figure in which we have 4 symmetrical petals An owl musket appears here to explain us that after completing the above design, you can use a color pencil with a ruler or compass to trace its boundary. This will make the design stand out from the supporting lines and arcs. Page number 141. This method of constructing the perpendicular bisector is not only geometrically exact but also a practical way to construct it accurately. This method to find the midpoint of a line segment is more accurate than measuring the length using a marked scale. Construction of a 90-degree angle at a given point. Can we extend the method of constructing the perpendicular bisector to construct a 90-degree angle at any point on a line? Draw a line and mark a point O on it. Construct a 90-degree angle at a point O. Here we have a line with a point O on it. Find a segment of this line for which O is the midpoint. Extend the line on either side of O. Using a compass, mark 2 points X and Y at equal distance from O so that O is the midpoint of XY. On the right side, we have another picture on which we have O as the center and X and Y are two arcs marked at equal distance from O. The perpendicular bisector of XY will pass through O and is perpendicular to the given line. In this case, do we need to draw two pairs of intersecting arcs to get the perpendicular bisector of XY? No, we don't. We already have one point O lying on the perpendicular bisector. Figure 6.2 and 6.3 describe the steps to construct a 90-degree angle at a given point on a line. Here we have another picture in which we find O is the center of the line and X and Y are two arcs cut from O at equal distances. With the help of the point X, we have an arc cut above XY, and with the same radius from point Y, we have the previous arc cut to intersect at point A. Now we join AO, which forms the perpendicular bisector for line XY. Construction methods in Sulbha Sutras. Ancient mathematicians from different civilizations, including India, knew exact procedures to construct perpendiculars and perpendicular bisectors. In India, the earliest known text containing these methods are the Sulbha Sutras. These are ancient geometry texts dealing with the construction of fire altars for rituals. The Sulbha Sutras are part of one of the 6 Vedangas, a term that literally means limbs of the Vedas. The Sulbhas contain the methods that we developed earlier to construct a perpendicular and the perpendicular bisector. Page number 142. All the construction methods in the Sulbha Sutras make use of the different kind of compass from what you have used a rope. A rope can be used to draw circles or arcs. This can also be stretched to form a straight line. In addition, the Sulbha Sutras also contain other methods to construct perpendicular lines. Here is an interesting construction of the perpendicular bisector using a rope. Katyana Sulbha Sutra 1.2. Let XY be the given line segment drawn on the ground, from which we need to construct a perpendicular bisector. Fix a small pole or peg vertically into the ground at each point X and Y. Take a sufficiently long rope. Make 2 loops at its ends. Without taking into account the parts of the rope that has gone into the loops, fold the rope into half to find and mark its midpoint. Fasten the two loops at the ends of the rope to the poles at X and Y. On the right side of the page, we are provided with a picture in which a rope is being stretched with both the hands. Fasten the two loops at the ends of the rope to the poles at X and Y. Pull the midpoint of the rope above XY as given in the figure such that the two parts of the rope on either side are fully stretched. Mark this position of the midpoint as A. On the right side of the page, the process has been given in which we can find XY is the line segment and the rope is forming a midpoint at A when stretched. Now similarly, pull the midpoint of the rope below XY as given in the figure such that the two parts of the rope on either side are fully stretched. Mark this position of the midpoint as B. AB is the required perpendicular bisector. On the right side, we again have a figure in which the process is repeated and a point B is marked with the help of the stretching the rope with the help of line segment XY. Figure it out. Question number 1. Justify why AB in figure 6.4 is the perpendicular bisector. Question number 2. Can you think of different methods to construct a 90-degree angle at a given point on a line using a rope? Page number 143. Angle bisection for a design. How do we construct this figure? Here, there is a figure with 8 floral petals which are symmetrical in shape. The supporting lines for this figure will appear like this. In this, we have a figure. We find that two pairs of lines are perpendicular to each other, and again we have another pair of lines which are perpendicular to each other, thus forming 8 line segments with 4 intersecting lines. What is the angle between two adjacent lines? We need the angle between every pair of adjacent lines to be equal, since 360 degrees is equally divided into 8 parts. Every angle is 45 degrees. How do we construct a 45 degrees angle using only a ruler and a compass? We know how to construct a 90-degree angle. If we can divide it into two equal parts or bisect it, then we get a 45-degree angle. We will now develop a general method to bisect any angle. Consider an angle XOY. Here we have a picture of angle XOY. We can bisect it if we can draw two congruent triangles, triangle OBC and triangle OAC as given in the figure. Then angle BOC is equal to angle AOC. On the right side of the page, we have a picture of angle XOY in which OC is the angle bisector and we have points B and A on line segments OX and OY with CB and CA joined. Page number 144. How do we construct these congruent triangles given the angle? If A and B are marked such that OA is equal to OB and if C is chosen such that BC is equal to AC, then by the SSS congruence condition, triangle OBC is congruent to triangle OAC. So we can bisect an angle as follows. Steps for angle bisection. First, mark points A and B such that OA is equal to OB. Here we have a picture in which we can find angle XOY. From O, one arc is cut at point B. With the same radius, an arc is cut on OY at point A. Step number 2. Choosing any sufficiently long radius, cut arcs from A and B, keeping the radius same. Mark the point of intersection as C. Step number 3. OC bisects angle AOB. Again, we have a picture here with angle XOY, in which we have two arcs B and A. From these 2 points and same radius, we again cut arc to meet at point C, and OC is joined, which forms the angle bisector. So, a 45 degrees angle can be constructed by first constructing a 90-degree angle and then bisecting it. Figure it out. Question number 1. Construct at least 4 different angles. Draw their bisectors. Question number 2. Construct the 8-petaled figure given in figure 6.5. Question number 3. In step 2 of angle bisection, if arcs of equal radius are drawn on the other side as given in the figure, will the line OC still be an angle bisector? Explore this through construction and then justify your answer. Here we are provided with a picture in which we can find an angle XOY and two arcs on line OX and OY with points B and A. We also have a point of intersection at C and CO is joined. Question number 4. What are the other angles that can be constructed using angle bisection? Can you construct 65.5 degrees angle? Question number 5. Come up with a method to construct the angle bisector using a rope. Page number 145. Question number 6. Construct the following figure. Here we are provided with a picture in which we have 4 petals of maximum possible size inside a square. How do we construct the petals so that they are of the maximum possible size within a given square? Repeating units and repeating angles. Construct the following figure. We have a picture here made up of 5 sectors, 3 in one direction and 2 in the opposite direction between them, without leaving any gap. This is figure 6.6. In this figure, there is a single unit repeating itself. To construct this figure, we need to make exact copies of this unit in 2 different orientations. Here we have another picture in which you can find 2 sector-shaped figures in different orientations. In order to make exact copies, all the units must have the same arm length and the same angle between the arms. We can ensure equal arm lengths using a compass. But how do we ensure equal angles? Let us develop a method to create an exact copy of a given angle. Draw an angle. Create a copy of this angle using only a ruler and compass. Here we can find a picture of an angle with name A. Page number 146. You must have developed your own method. Here is one simple approach. Steps of construction to copy an angle. First, we have a picture of an angle A. To construct this, first you draw a line with point X on it. In the second step, from point A, we take an arc and cut on the arms of the angle to intersect at point B and C. Draw an arc from A. This gives us 3 points that form the isosceles triangle ABC. Step number 3. Draw an arc of same radius from X. Step number 4. Measure BC using a compass. Transfer this length on the arc from Z to get YZ is equal to BC. Page number 147. Step 5. By the SSS congruence condition, triangle ABC is congruent to triangle XYZ. So, angle A is equal to angle X. We can find the picture of the same here representing triangle ABC congruent to triangle XYZ. Figure it out. Question number 1. Construct at least 4 different angles in different orientations without taking any measurement. Make a copy of all these angles. Here we have picture of 4 different angles in different orientations. Question number 2. Construct the figure 6.6. This procedure to copy an angle finds an important application in constructing parallel lines using only a ruler and compass. Construction of a line parallel to the given line. Recall that in the construction using a ruler and a set square, we constructed equal corresponding angles to get parallel lines. How do we implement this idea using a ruler and a compass? Suppose there is a line M to which we need to draw a parallel line. We construct a line L that intersects M. Line L will serve as a transversal to line M and to the line parallel to M that we are going to construct. On the right side, we have a picture in which line M is cut by line L to form an angle A at point A. Let us choose a point B on line L through which we are going to draw the parallel line. This parallel line must make the same corresponding angle as given in the figure. This can be done by copying the angle between M and L. On the right side of the page, we have 2 parallel lines and line L cuts these lines at A and B, making equal angles angle A. Page number 148. Here is a step-by-step procedure for carrying this out. In figure 6.8 and 6.9, respectively, we find to construct arcs of equal radius from A and B and then transfer the length CD to the arc from F. In figure 6.10, we have 2 parallel lines N and M intersected by line L at points B and A. From point A and B, 2 arcs are cut at points CD and EF. Figures 6.7 to 6.10 describe a method to construct a line parallel to the given line. Figure it out. Question number 1. Construct 4 pairs of parallel lines in different orientations. Question number 2. Construct the following figure. Here we have a picture in which we can find a star having 8 symmetrical triangles. Each triangle is subdivided into 2, out of which 1 is shaded. And the points also are named as A, B, C, D, E, F, G, H. And we also have points named as outside the triangle S, T, U, V, W, X, Y and Z. Page number 149. Arc designs. Trefoil arc. Have you noticed this kind of beautiful arc? Here we have beautiful pictures of Diwane Am Red Fort and Central Park, New York City. The links for the source of the image have also been provided of the same. The links provided are https://commons.wikipedia.org/w/index php curid equal to 28374,748 Diwane Am Red Fort. Another link provided is https://commons.wiki.org/wiki/file:/central_a.jpg Central Park, New York City. How did they make these arcs? The first step is to be able to draw them on a plain surface such as paper or stone. Construct this arc shape on a piece of paper. Let us think about the support lines this figure will need. We have a figure to draw these arcs on the right side with lines AD and BC as parallel and with small arcs at AB and CD and also an arc joining CB. For symmetry, we should have AB is equal to CD and angle BAD is equal to angle CDA. How would you construct these support lines? We have a line segment AD here, and on the right side we have a line segment AD with equal angles marked formed as angle BAD and angle ADC. Construct equal angles at A and D. Mark B and C such that AB is equal to CD. Use these support lines to construct an arc. If required, adjust the radii of the arcs to make the arc look more aesthetically pleasing. Page number 150. A pointed arc. Some arcs look like this. Here we have another picture of Diwane Am Red Fort. The link of the source of the image has been provided here, which reads https://en.m.wikipedia.org/wiki/file: Diwane Am, red_Delhi_2.jpg. How do we construct this shape? What supporting lines will you use to draw this arc? Remember, wavy wave from the grade 6 textbook. The supporting lines are just two line segments of equal lengths. We have a picture of line segments on which the wavy wave structure has been constructed to give the shape of the arc. If their midpoints are marked, will you be able to construct a pointed arc? Here we have two intersecting lines with 2 points at equal distance marked on it in figure 6.11. Page number 151. Figure it out. Question number 1. Use support lines in figure 6.11 to construct a pointed arc. Make different arcs by changing the radius of the arcs. Question number 2. Make your own arc designs. Regular hexagons. Recall that a regular polygon has equal sides and equal angles. A regular polygon with 3 sides is an equilateral triangle, and a regular polygon with 4 sides is a square. We have constructed these figures earlier. How do we construct a regular pentagon? 5-sided figure. And a regular hexagon? 6-sided figure. To begin with, try to construct a pentagon and hexagon with equal side lengths. We are provided with a picture of a pentagon and a hexagon having equal sides and equal angles. To construct a regular pentagon, we first need to have a better understanding of triangles and pentagons. We will discuss this in later years. However, constructing a regular hexagon is within our reach. Can we break a regular hexagon into smaller pieces that can be constructed? Regular hexagon and equilateral triangles. What happens when we join the opposite points of a regular hexagon? Since a regular hexagon has equal sides and angles, can we expect a figure like this? Will all the triangles in the figure be equilateral triangles? To answer these questions, we will reverse our approach. Can 6 congruent equilateral triangles be placed together as in the figure 6.12? If yes, will it result in a regular hexagon? Here we are provided in figure 6.12 a hexagon formed by making 6 equilateral triangles. The hexagon is named as A, B, C, D, E, F with the point and the center as O. Page number 152. If 6 congruent equilateral triangles can indeed be placed as shown in figure 6.12, then the sides of the resulting hexagon are equal and their angles are 60 plus 60 is equal to 120. How? So what we really need to examine is whether 6 congruent equilateral triangles can fit this way without overlapping and without leaving any gap around the center. We have defined a degree by taking the complete angle around a point to be 360 degrees. So, all the angles around the center should add up to 360 degrees. Consider this figure. Will the 70-degree angle fit into the gap? What is the gap angle? Angle AOI. We have 40 degrees plus 60 degrees plus 50 degrees plus 30 degrees plus 40 degrees plus 90 degrees plus gap angle is equal to 360 degrees. Use this to determine whether the 70-degree angle fits the gap. Thus, if there are angles that add up to 360 degrees, their vertices can be joined together at a single point such that A. The angles do not overlap and B. They completely cover the region around the point. Since each angle in an equilateral triangle is 60 degrees, 6 such angles add up to 360 degrees. Therefore, 6 congruent triangles can be arranged as given in figure 6.12. Here we have a picture in which the angles have been joined together 40 degrees, 60 degrees, 50 degrees, 30 degrees, 40 degrees and 90 degrees, and with a gap angle of 70 degrees is to be placed at point O. In figure 6.12, can you explain why AOD, BOE and COF are straight lines? Construct a regular hexagon with a side length 4 cm using a ruler and a compass. We can construct a regular hexagon more directly if we can construct a 120-degree angle using a ruler and a compass. How do we do it? This can be done if we can construct a 60-degree angle. Here there is a picture of a straight line with an arm length on it making an angle of 60 degrees. If we construct 60 degrees, on the right side we have another angle of 120 degrees. Page number 153. Construction of a 60-degree angle. how do we construct a 60-degree angle? We get a 60-degree angle if we construct an equilateral triangle. We can use the following steps for this. Suppose we need a 60-degree angle at point A on a line segment AX. Step 1. Construct an arc with center A and any radius. In figure, this has been represented with line AX and an arc from A has been drawn to intersect the line at B. Step 2. With the same radius, cut another arc from B that meets the first arc. Let C be the point at which the arcs meet. This has been represented in the figure given here. We have angle CAX is equal to 60 degrees. Why is angle CAX is equal to 60 degrees? Is there an equilateral triangle here? We can use these ideas to construct a regular hexagon. The figure of a regular hexagon is given here. Construct a regular hexagon of side length 5 centimeters. Page number 154. Related constructions. Construction of 30 degrees and 15 degrees angles. How will you construct 30 degree and 15 degree angles? 6-pointed star. Construct the following 6-pointed star. Note that it has a rotational symmetry. Here there is a picture of a 6-pointed star. The hint provided here is we have a hexagon and 6 equilateral triangles at 6 sides of the regular hexagon, which are named as triangle AGH, BHI, ICJ, JDK, KEL and LFG. Do you find a hexagon here? Are the 6 triangles forming the 6 points of the star triangle AGH, triangle BHI, triangle CIJ, triangle DJK, triangle ELK, triangle FLG equilateral? Why? The hint provided is find the angles. Figure it out. Question number 1. Construct the following figures. In A, we have an inflexed arc in which we find 2 circular arcs with parallel sides. In figure B, the fun part about this figure is that it can also be constructed using only a compass. Can you do it? Here, the figure is one circle with 6 circular petals around it. Page number 155. We have in C one circle and a hexagon is placed inside it. In D, we have 6 circles touching each other of same size. In figure E, we have a hexagon in which we can find 7 stars placed inside it without leaving any gap. Question number 2. Optical illusion. Do you notice anything interesting about the following figure? How does this happen? Recreate this in your notebook. Question number 2. Optical illusion. Do you notice anything interesting about the following figure? How does this happen? Recreate this in your notebook. Here we are provided with a figure which gives an illusion of 2 triangles, but none of the triangles are drawn with the line segments. Question number 3. Construct this figure. Hint provided is find the angles in this figure. Here we find a hexagonal shape in which a star is inserted. Question number 4. Draw a line L and mark a point P anywhere outside the line. Construct a perpendicular to the given line L through P. Hint provided is find a line segment on L whose perpendicular bisector passes through P. 6.2 Tiling. Tangrams are puzzles that originated in China. They make use of 7 pieces obtained by dividing a square as given here. For the problems ahead, we need these 7 tangram pieces. These are provided at the end of the book, or by observing the figure, you could make cardboard cutouts of the pieces. Here we are provided with a picture of square cutout in which we can locate all the 7 pieces of tangram named as A, B, C, D, E, F and G. Page number 156. We can form interesting pieces by rearranging the tangram pieces. Here is an arrow. We have a picture of an arrow formed by joining the tangram pieces. Figure it out. How can the tangram pieces be rearranged to form each of the following figures? We have 10 figures formed with the help of tangrams like alphabets C, M. We have geometrical patterns, figure of a cat, swan, fish, man and a boy. Page number 157. Covering a region using a set of shapes without gaps or overlaps is called tiling. Consider a rectangular grid made of unit squares. We call this a 4 by 6 grid since it has 4 rows and 6 columns. We are provided with a picture in which we can locate 4 by 6 grid having 4 rows and 6 columns. Can a 4 by 6 grid be tiled using multiple copies of 2 by 1 tiles? We are allowed to rotate a 2 by 1 tile and use it. Here we have pictures of 2 by 1 tiles. One is in the vertical pattern and another is in horizontal pattern with vertical tile and horizontal tile titles. Here is one way. We have 4 by 6 grid in which the pattern of placing the vertical tile and horizontal tile has been represented. Obviously, this is not the only tiling possible. Can a 4 by 7 grid be tiled using 2 by 1 tiles? What about a 5 by 7 grid? To find that there is no way to tile a 5 by 7 grid using 2 by 1 tiles, observe that this grid has 35 unit squares. Each tile covers exactly 2 unit squares. Page number 158. Complete the justification. Is an M by N grid tileable with 2 by 1 tiles? If both M and N are even. If yes, come up with a general strategy to tile it. One general strategy for this case is to cover each column with vertical tiles. This is possible because the number of rows is even. Here we have a picture in which the process is explained by representing it with even number of tiles. Is an M by N grid tileable with 2 by 1 tiles? If one of the M and N is even and the other is odd. If yes, come up with a general strategy to tile it. Is an M by N grid tileable with 2 by 1 tiles? If both M and N are odd, give reasons. Here is a 5 by 3 grid with a unit square removed. Now, it has an even number of unit squares. Is it tileable with 2 by 1 tiles? Here we have a picture of 5 by 3 grid with 1 unit square removed. Is the following region tileable with 2 by 1 tiles? In this we have a picture of 5 by 3 grid with one of the tiles in the second row missing. Page number 159. What about this one? Here we have another picture of 5 by 3 tiles arranged, and with one of the tiles in the first row is missing. Were you able to tile this? How can we be sure that this is not tileable? Can you find another unit square that when removed from a 5 by 3 grid makes it non-tileable? There is an interesting way to look at these questions. For any tiling problem of this kind, we can create a similar problem with the unit squares colored black and white, so that black squares have only white neighbors and white squares have only black neighbors. For the tiling problem in figure 6.13, we get the following. Here we have pictures of these tiles given here. First one has 5 by 3 grid, which is plain grid, and region to be tiled is represented with one of the tiles missing in the first row. Beside it, we have black and white grid, which are alternately white and black, and 5 by 3 pattern, and the tiles given here are of 2 by 1. We have one in horizontal and other in vertical tile in both the cases. This is figure 6.14. In the black and white region, the problem is to tile the region with the 2 by 1 black and white tiles so that each black square of a tile sits on the black square of the grid and each white square sits on the white square. If the plain grid is tileable, is the black and white grid tileable? If the black and white grid is tileable, is the plain grid tileable? It can be found that the answer to both the question is yes. Page number 160. Is the black and white region in figure 6.14 tileable? Any region tiled with black and white tiles must have an equal number of black tiles and white tiles. Since the black and white region in figure 6.14 has 8 white squares and 6 black squares, it can never be tiled with these tiles. Use this idea to find another unit square that, when removed from a 5 by 3 grid, makes it non-tileable. Isn't it surprising how, by introducing colors and making the problem more complicated, it becomes easier to tackle? What a creative way of looking at the problem. Figure it out. Are the following tilings possible? In the first question, region to be tiled is given, in which we have 12 tiles arranged and one tile having only 3 tiles is placed beside it. In the second question, region to be tiled is given in the picture and one tile at both the corners opposite to each other are missing, and one tile having 2 by 1 tile is placed beside it, tiling the entire plane. So far, we have seen how to tile a given region. What about tiling the entire plane? Can you think of a shape whose copies can tile the entire plane? Clearly, squares can. Page number 161. Here we have a picture of blue tiles which are 12 in number and they are arranged in 3 rows and 4 columns. Are there other regular polygons that can tile the plane? What about equilateral triangles? Here we have a picture of equilateral triangles which are placed just adjacent to each other. Tiling with equilateral triangles gives the possibility of tiling with another regular polygon. A plane can be tiled using regular hexagons as well. Here we have a picture of tiling with regular hexagons. They have been placed adjacent to each other without any gap. A plane can also be tiled using more than one shape and using non-regular polygons. People such as the great Dutch artist Escher in 1898 to 1972, whose works explored mathematical themes such as tiling, have come up with creative ways of tiling a plane with animal shapes. Here are some examples. In A, we have triangles and squares which have been placed adjacent to each other and they are used for tiling. In B, we find geometrical patterns which have been used for tiling in different colors. Page number 162. Here in figure C, we have a tiling view made up of green and pink fishes. They have been used for the tiling purpose. And in D pattern, we have horse with rider. They have been used to form the tile. Mathematicians are still exploring various ways of tiling the plane. Tiling B was found as recently as 2023. Have you noticed tilings in daily life? They are often used in buildings and in designs. Tilings are found in nature too. The front face of a beehives and some wasp nests are tiled using hexagonal cells. Here we have a picture of a beehive and a bee. These cells are used by the insects to keep their eggs, larvae and pupae safe, as well as to store food. Because the region is tiled, no space is wasted. Scientists still wonder how bees and wasps are able to make hexagonal cells. Next time you find any tiling, pay closer attention to it. Tiling is still one of the most exciting and active areas of research in geometry. Page number 163. Summary. First point. A division of a line segment or any geometrical quantity into two identical parts is called bisection. Point number 2. Any point that is of equal distance from the two endpoints of a given line segment lies on its perpendicular bisector. This property can be used to construct the perpendicular bisector using a ruler and compass. Point number 3. The method of constructing the perpendicular bisector can be modified to draw a 90-degree angle at any point on a line using only a ruler and compass. Point number 4. An angle can be bisected and copied using the congruence properties of triangles. Point number 5. A 60-degree angle can be constructed using a ruler and compass by constructing an equilateral triangle. Point number 6. Covering a region using a set of shapes without gaps or overlaps is called tiling. Chapter 6 ends here.
Ganit Prakash, Part 2. You were just listening to this audiobook, Textbook of Mathematics for Grade 7. Narration, Swarnlata Sharma. Sound recordist, Prasoon Kumar. Assistants in production, Amarjeet Sarkar. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.